Welcome! In this session, we'll tackle LeetCode problem number 358, titled Rearrange string k distance apart. This interesting problem challenges us to rearrange characters in a string such that the same characters are separated by at least k distance. We'll explore the problem requirements, possible approaches, and step-by-step solutions. Let's dive in. In this problem, we are given a string s and a positive integer k. The goal is to rearrange the characters in the string such that the same characters are at least k distance apart. If it's not possible to rearrange the string to satisfy this condition, we simply return an empty string. The input consists of the string s, which contains only lowercase English letters, and the integer k, which can range from 1 to the length of the string. The output is either a valid rearranged string that satisfies the distance condition or an empty string if no valid arrangement exists. For example, if the input string is s equals 8 and k equals 3, we need to rearrange the string so that no two identical characters are closer than 3 positions apart. For the input s equals 8 and k equals 3, one valid output could be AppCap. In this arrangement, each character appears only once within any window of size k, satisfying the condition. Since the input string contains 3 distinct characters a, b, and c each appearing twice, we can distribute them evenly to maintain the required distance. While this is one possible solution, other valid arrangements may also exist, as long as they meet the k distance requirement. On the other hand, for the input s equals a and k equals 3, it is impossible to find any rearrangement where all the characters are at least 3 positions apart, so the output would be an empty string. This impossibility arises in the s equals a example because the string contains 3 characters, but there aren't enough other characters in the string to separate them by at least 3 positions. Therefore, no valid rearrangement exists, and the function returns an empty string. However, consider the case where s equals 8 and k equals 2. Here, the input contains 3 characters, 2 b characters, 2 c characters, and 1 d. A valid output for this input is a backabad. In the output of backabad, each it is separated by at least 2 positions, satisfying the condition that no two identical characters are closer than k equals 2. The way the other characters are arranged also ensures that the condition is met. It's important to note that this is just one valid solution. There may be other ways to rearrange the string that also satisfy the distance constraint. The constraints for this problem specify that the length of s can go up to 10,000 characters, and s contains only lowercase English letters. The value of k is always between 1 and the length of s. These constraints ensure that the problem is well defined, but they also indicate the need for an efficient solution. Now let's discuss some important edge cases. First, if k equals 1, the condition is automatically satisfied because there is no restriction on the distance between identical characters. Any permutation of the string will be valid. For example, if s equals ab and k equals 1, outputs like abba or ba are acceptable. Second, if all characters in the string are the same, such as s equals aaa, a valid rearrangement is only possible if k equals 1. For any k greater than 1, it becomes impossible to rearrange the string, so the output would be an empty string. Finally, if k is greater than the length of the string, it is always impossible to satisfy the condition. For example, if s equals abc and k equals 5, the output must be an empty string because the characters cannot be spaced far enough apart. These edge cases help clarify the behavior of the solution under different scenarios. To solve the problem of rearranging a string such that no two identical characters are closer than k positions apart, we need to explore different approaches. One option is the brute force approach. The intuition here is straightforward: generate all possible permutations of the string and then check each permutation to see if it satisfies the k-distance condition. This would involve generating all permutations of the input string, iterating through each one to ensure that the same characters are separated by at least k positions, and returning the first valid result. However, this approach is highly inefficient. Generating permutations has a factorial time complexity, O(n), due to the sheer number of possible arrangements. Additionally, verifying each permutation introduces an extra O(n) factor. This makes the brute force method impractical for larger strings, as the computation quickly becomes infeasible. While simple to understand, the inefficiency of this method means we need to consider more scalable strategies.
A more optimized and feasible solution is the greedy approach using a max heap.
The key intuition here is that characters with the highest frequency are the most constrained, as they need the most spacing. Therefore, we prioritize placing these characters first. To implement this, we start by calculating the frequency of each character in the string. These frequencies are then stored in a max heap, where the character with the highest frequency is always at the top. The solution is built by repeatedly selecting the most frequent character from the heap, placing it in the result, and temporarily storing it in a cooling queue with its frequency reduced by 1. This ensures that the character cannot be reused until k positions have passed. After k iterations, characters in the cooling queue are reinserted into the heap if they still have remaining frequency. If at any point the heap becomes empty before the result is fully constructed, it means the arrangement is not possible and we return an empty string. This approach is efficient because the heap operations and frequency management keep the process streamlined, resulting in a time complexity of n*log a, where n is the string length and a is the number of unique characters. The space complexity is also manageable, making this strategy both efficient and practical.
Another alternative to consider is the counting sort with buckets approach.
Here, the intuition is to use a bucket-based strategy to ensure characters are spaced k positions apart.
First, the frequencies of all characters are counted and then sorted. Characters are then assigned to positions spaced k apart using a bucket structure.
If at any point a character cannot be placed, it implies that the arrangement is not possible, and we return an empty string. This method has a time complexity of n plus a*log a, where is the number of unique characters, and requires n space.
However, despite its comparable efficiency, this approach was not chosen.
The bucket sort method can be harder to implement and debug, especially when handling edge cases.
Its added complexity makes it less appealing compared to the heap-based solution, which provides a more straightforward way to manage the placement constraints. The chosen strategy for solving this problem is the greedy approach with a max heap. This method strikes the right balance between efficiency and ease of implementation.
By prioritizing the placement of the most constrained characters, those with the highest frequencies, the heap ensures that the k-distance condition is met. Additionally, the heap-based method naturally handles edge cases by verifying if the heap is empty before the result is complete, which simplifies the process. When comparing the approaches, the heap-based strategy is exponentially faster than the brute force method, which is computationally infeasible for large inputs. While the bucket sort method has a comparable time complexity, the heap approach is more intuitive and requires fewer edge case adjustments, making it easier to implement. Although the heap-based solution uses slightly more space, the difference is negligible for typical input sizes. Overall, the greedy approach with a max heap is efficient, scalable, and straightforward, making it the optimal choice for this problem. This problem challenges us to rearrange the characters of a string so that the same characters are separated by at least k positions.
If this rearrangement isn't possible, we return an empty string. For example, given the input string s equals ape with k equals 3, one possible output is apcap.
The key difficulty lies in balancing the frequency of characters while ensuring the distance constraint is met. To achieve this, we start by counting the frequency of each character in the string using a hash map.
For instance, if s equals aap, the frequency map is a3, b2, c1.
This frequency count helps us determine which characters are the most frequent, as these characters must be spaced out first to avoid violating the k-distance requirement.
This step lays the groundwork for the rest of the algorithm.
Once we have the frequency map, the next step is to use a max heap to prioritize the characters based on their frequency. A max heap, or priority queue, allows us to efficiently retrieve the character with the highest frequency, which is critical for spacing characters properly. In Python, we can create this max heap by inserting the negative of each frequency, like so: max_heap equals frequent char for char frequency and frequency_map.items, and then using heap.heapify max_heap. This ensures that the character with the highest frequency is always at the top of the heap. Additionally, we introduce a greedy approach for rearranging the string.
We initialize an empty result string and a waiting queue to keep track of characters that are cooling down. As we process the heap, we pop the most frequent character, append it to the result, and decrement its frequency.
If the character still has remaining occurrences, it is added to the waiting queue with a cooldown timer of k positions, ensuring it isn't reused prematurely. When a character's cooldown expires, meaning its timer reaches 0, it can be reinserted into the heap.
Here's an example to illustrate the process. For the input s equals a app with k equals 3, the initial max heap is -3 a, -2 b, -1 c. The result starts empty, and the waiting queue is also empty. First, we pop a from the heap, append it to the result, and add it to the waiting queue with a cooldown. The result becomes a, and the waiting queue holds 2 a. Next, we pop b, append it to the result, and add it to the waiting queue. The process continues until the heap is empty and all characters are used. Finally, we validate the result. If the result length matches the input string, we return it. Otherwise, if any constraints could not be satisfied, we return an empty string. This ensures that the output is either a valid rearranged string or an indication that rearrangement was not possible. In this algorithm, there are several edge cases to consider. If k is 0, no rearrangement is needed, so we simply return the input string. If the string length is less than k, it's impossible to satisfy the distance constraint, and we return an empty string. For strings with only one unique character, such as AAA, if k is greater than 1, the constraint cannot be met, so we return an empty string. Regarding the data structures used, we rely on a hash map to count character frequencies, which takes O(n) time. The max heap helps us efficiently retrieve the most frequent character, with each operation taking O log n. Finally, the queue manages cooldowns, requiring O(n) operations. Altogether, the time complexity of the algorithm is O(n) log n, accounting for heap operations and result construction, while the space complexity is O(n) due to the hash map, heap, and queue. This makes the solution both time and space efficient. To see how this works in practice, let's walk through the example with s equals a app and k equals 3. We start with the frequency map, a 3, b, 2, c, 1, and the max heap, -3, a, -2, b, -1, c. First, we pop a from the heap and append it to the result, making the result a. A is added to the waiting queue with a cooldown of 3. Next, we pop b, append it to the result, and add it to the waiting queue with a cooldown. The result becomes a b. Then, we pop c, append it to the result, and update the waiting queue. When the cooldown for it expires, it is reinserted into the heap and processed again. This cycle continues until both the heap and queue are empty. The final result is AppCac. If at any point it had been impossible to construct a valid string, we would return an empty string instead. To solve the problem of rearranging a string with a k-distance constraint, we start by importing necessary libraries. We use the counter class from the collections module to count character frequencies, a deque to implement the wait queue, and heap to manage our max heap. The rearrange string function begins by handling the edge case where k is 0, in that case, no rearrangement is needed, so we return the string as is. Next, we compute the frequency of each character in the string using counter, which gives us a mapping of characters to their counts. With this frequency map, we construct a max heap. Since Python's heap library only supports min heaps, we negate the frequencies to simulate a max heap. This helps us efficiently retrieve characters with the highest frequency. After heapifying the list, we initialize a deque as a wait queue to enforce the k-distance constraint and an empty result list to build the final output string. Then, we enter a while loop that continues as long as we have characters in the heap or in the wait queue. If the max heap is empty but there are still characters waiting in the queue, it means the constraints cannot be satisfied, and we return an empty string. Otherwise, we pop the most frequent character from the heap and append it to the result list. After appending the most frequent character to the result, we update its frequency to reflect that one occurrence has been used. Since the frequencies in the heap are stored as negatives, we increment the value to move it closer to 0 and then add the character with its updated frequency to the wait queue. The wait queue ensures that a character is delayed by at least k positions before being reintroduced. If the wait queue grows to a size of k, this means the character at the front of the queue is now eligible to be reused. At this point, we remove it from the queue and check its frequency. If the frequency indicates there are still occurrences left, we push it back into the max heap. This process ensures that characters are spaced apart by at least k positions whenever possible.
Finally, when the loop ends, we join all the characters in the result list to form the rearranged string and return it. This approach effectively balances frequency constraints with the k-distance requirement, ensuring the solution is both valid and efficient. Here, we start by defining the rearrange string method, which takes a string s and an integer k. If k is 0, we return the string as it is, since no rearrangement is needed. Next, we move to step 1, where we count the frequency of each character in the string. This is done using a hash map, where the key is the character and the value is its frequency. Once we have the frequency map, we proceed to step 2, where we build a max heap to prioritize characters with higher frequencies. This is implemented using a priority queue with a custom comparator that sorts entries in descending order of their frequency. In step 3, we introduce a queue to enforce the k-distance constraint, which helps ensure that the same character is not placed too close together. We also initialize a string builder to construct the final result string. The main logic begins with a loop that continues as long as there are characters in the max heap or the wait queue. If the max heap is empty but the wait queue still has characters, it means it's impossible to rearrange the string with the given constraints, so we return an empty string as the result. When the max heap is not empty, we move to step 5, where we remove the most frequent character from the heap using poll. This character is added to the result string using the string builder. In step 6, we decrease the frequency of this character by 1 and add it to the wait queue. The wait queue holds characters temporarily to enforce the k-distance constraint. Next, in step 7, we check if the wait queue has reached the size of k. If it has, we remove the character at the front of the queue. If this character still has a non-zero frequency, we reinsert it back into the max heap so it can be used again later. This process continues until both the max heap and wait queue are empty. Finally, the constructed string in the string builder is returned. This ensures that the characters in the string are rearranged such that no two identical characters are less than k distance apart, or an empty string is returned if rearrangement is not possible. To solve this problem, we start by examining a basic case where the input string is 8 and k is set to 2. First, we count the frequency of each character in the string using Python's counter. This gives us the result, a 2, b, 2, c, 2, indicating that each character appears twice. Next, we construct a max heap based on these frequencies. Since Python's heap library only supports a min heap, we invert the frequencies to simulate a max heap. The resulting heap is -2, a, -2b, -2c, where the most frequent characters are prioritized. Additionally, we initialize an empty D called wait_q, which will help us enforce the k-distance rule, and an empty result list to build the final output string. Now we begin the main processing loop by popping the most frequent character from the max heap. We start with -2, append it to the result list, reduce its frequency to -1, and add it to the wait_q. At this point, the result list is and the wait_q contains -1, We repeat this process for the next two most frequent characters. Popping -2b, we append b to the result, reduce its frequency to -1, and add it to the wait_q. The result becomes b, and the wait_q is updated to -1, -1b. Finally, we pop -2c, append c to the result, reduce its frequency to -1, and add it to the wait_q. The result now holds b, c, and the wait_q contains -1, -1b, -1c. As the wait_q reaches the size of k, we can start reintroducing characters back into the max heap. The oldest character in the wait_q, -1, is removed and pushed back into the max heap since its frequency is still less than 0. The max heap now contains -1, while the wait_q holds -1b, -1c. We continue processing characters until all are handled. During subsequent iterations, we appended b and c again to the result list, maintaining the k-distance constraint. The final result list becomes b, c, which successfully rearranges the string so that no two identical characters are less than k equals 2 positions apart. The output of this example is abcap. For edge cases like k equals 0, no rearrangement is required.
For instance, with input ob and k equals 0, we simply return the string as is, resulting in ob. Next, we consider an impossible case where the input string is ob and k is 3. We start by counting the character frequencies, which gives 3, b, 1. Using this, we build a max heap that prioritizes the most frequent characters, resulting in -3, -1, b. In the first iteration of the loop, we pop -3, append it to the result, reduce its frequency to -2, and add it to the wait underscore q. At this point, the result list is and the wait underscore q contains -2, In the next step, we pop -1, b, from the max heap, append b to the result, reduce its frequency to 0, and add it to the wait underscore q. The result list becomes b, and the wait underscore q now contains -2, 0, b. However, at this point, the max heap is empty, and the wait underscore q still holds -2, indicating that there are not enough remaining characters to satisfy the k equals 3 constraint. Since it's impossible to rearrange the string under this condition, we return an empty string as the output. The time complexity of our solution is influenced by several key operations. First, we calculate the frequency of each character in the input string using the counter function. This requires a single pass through the string, giving it a time complexity of O, n, where n is the length of the string. Next, we construct a max heap based on these character frequencies. To do this, we iterate over the frequency map, which contains c unique characters. Each insertion into the heap takes O log c, so the total time for heap construction is O c asterisk log c. These two steps set the foundation for the overall time complexity of the solution. The next critical step involves rearranging the characters to meet the k-distance condition. Here, we process each character in the string within a while loop. For each iteration, we pop the most frequent character from the heap, which takes O log c, and push it into a temporary wait q and O1 operation. If the wait q reaches size k, we reinsert its front element into the heap, incurring another O log c for the heap operation. Since every character is pushed and popped from the heap at most once, the total cost of all heap operations in this step is O n asterisk log c. When we combine this with the earlier steps, the overall time complexity becomes O n plus O c asterisk log c plus O n asterisk log c, which simplifies to O n asterisk log c, because c, the number of unique characters, is typically much smaller than n. Now let's discuss space complexity. The first factor is the frequency map, which stores the count of each unique character, requiring O c space. The second factor is the max heap, which holds up to c elements, also requiring O c space. Then, we have the wait q, which holds at most k elements at any given time, resulting in an O k space requirement. Lastly, we have the result list, which stores the rearranged characters and grows to the same size as the input string, requiring O n space. These components together result in a total space complexity of O c plus k plus n. When combining all these space requirements, we see that the total space complexity is O c plus k plus n. However, since c is usually much smaller than n and k is bounded by n, the space complexity simplifies to O n in the worst case. Comparing this to a naive approach, which would generate all permutations of the string to check the k-distance condition, the naive method would require O n time for permutations in O n asterisk n overall, which is computationally infeasible for even moderately sized strings. Our optimized solution avoids this by using a greedy strategy with a heap to efficiently select the most frequent valid character. This reduces the time complexity to O n asterisk log c, making it far more efficient. Let's analyze the best, average, and worst cases for this solution. In the best case, if k is 0, the input string can be returned directly, resulting in O n time and space complexities. In the average case, when k is greater than 0 and c is small relative to n, the time complexity is O n asterisk log c, and the space complexity remains O n. For the worst case, when k approaches n and all characters in the string are unique, the time complexity still holds at O n asterisk log c, and the space complexity remains O n, as the heap and wait q sizes are bounded by n. The mathematical justification for the overall time complexity lies in the heap operations during the while loop. Each character is pushed to and popped from the heap once, with each operation taking O log c. This leads to a total cost of O, n asterisk log, c, with additional terms like O, n, and O, c asterisk log, c, being asymptotically smaller. Thus, the final time complexity remains O, n asterisk log, c. When tackling this problem, there are a few common mistakes to watch out for. First, you must handle edge cases properly. For example, if the value of k exceeds the length of the string, it becomes impossible to rearrange characters to satisfy the k-distance condition. Neglecting this can lead to incorrect results, so always verify if the constraints are feasible before proceeding. Another common pitfall is relying on a greedy placement strategy without using a priority queue. This often fails when there are multiple high-frequency characters, as gaps can form that cannot be filled later. A max heap ensures that the most frequent characters are prioritized for placement, avoiding such issues. Additionally, when implementing the solution, some approaches forget to restore characters back into the heap after their cooldown period. This leads to incomplete or incorrect outputs. A better strategy is to use a queue to track characters during their cooldown and reinsert them once they are eligible. Finally, don't assume that all input strings are rearrangeable. For example, if you have an input like abgin k equals 3, it's impossible to rearrange it to meet the condition. Always verify feasibility by ensuring no character's frequency exceeds what's allowable given the constraints. Another frequent challenge is dealing with inefficient implementations. For instance, using nested loops or repeatedly recalculating frequencies can significantly increase time complexity. Instead, focus on efficient data structures like a max heap and a queue, which allow you to manage frequencies and placements in O, n log n, time. Additionally, there are several key insights to keep in mind for interviews. Problems involving character rearrangement often depend on frequency analysis combined with greedy methods, and heaps and queues are recurring tools for solving them. Be sure to test edge cases thoroughly, such as very short strings, large values of k, and scenarios where rearrangement is impossible. It's also important to communicate trade-offs during an interview. For example, you might compare using a heap versus sorting by frequency, explaining why one approach might be more optimal than the other depending on the scenario. Regarding complexity, aim to achieve O, n log n, time and O, n, space, and be prepared to explain how the heap and queue contribute to these bounds. Lastly, always clarify constraints with the interviewer, such as whether the input contains only lowercase letters, or if additional input validation is required. This problem has strong connections to other popular problems on LeetCode, which can help you see common patterns and strategies. For example, LeetCode 621, the task scheduler problem, involves a similar concept where tasks must be scheduled with a cooldown period of n units. Another related problem is LeetCode 767, reorganize string, where the goal is to rearrange characters such that no two adjacent characters are the same. LeetCode 451, sort characters by frequency, is a useful subproblem that focuses on analyzing frequencies, which is a key step in solving the k-distance rearrangement problem. Finally, there are variations of this problem, such as rearranging strings with additional constraints, like fixed positions or groups, which often appear in more advanced problems. Exploring these related problems can deepen your understanding of the patterns and techniques involved. There are also a few alternative approaches worth considering, each with its own advantages and trade-offs. One approach involves sorting characters by frequency and attempting to place them k-distance apart. This method can be simpler to implement but lacks the flexibility of a heap, especially when dynamic updates are needed during the placement process. Another option is a greedy strategy combined with bucket sort. Here, you group characters by frequency and distribute them across the string in k-distance intervals. While this can be more efficient for specific cases, it's generally less adaptable to problems with more complex constraints. Lastly, there's the brute force approach using backtracking, where you explore all possible permutations of the string to find one that satisfies the k-distance condition. However, this method is computationally expensive, with a time complexity of O, n, in the worst case, making it impractical for larger strings. Understanding the strengths and limitations of these approaches allows you to choose the most appropriate strategy based on the problem's requirements. Great job! To recap, we used a greedy approach with a priority queue to solve the problem efficiently. This problem showcased how to use heaps for managing constraints like k-distance ordering.
Remember to keep practicing similar problems to strengthen your problem-solving skills.
Thanks for watching, and I hope to see you in the next session. That's the end of this tutorial.
I hope you found this explanation helpful for understanding the solution to this LeetCode problem.
If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions.
Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have.
Thanks for watching, and happy coding!